All right, and we're going to wrap up the solutions of homework 4 by solving problem 4D. In this problem, we have the same beam as before, but this time the distributed load is only on the overhanging end. The distributed load is still a magnitude of 4 kips per foot, this time over a 4-foot distance. So again, anytime we do shear and moment diagrams, the very first step is we have to solve reactions. So we'll use the equations of equilibrium. First, sum of forces equals 0. We're going to make an assumption that the reaction at A and the reaction at B are both going upwards. So the sum of forces going down, we have 4 kips per foot times 4 feet. That's 16 kips going down equals R sub A going up plus R sub B going up. And that's what we can do with sum of the forces equals 0. We also have to do sum of moments equals 0. We're going to pick point A to sum moments about, and I'll mark that with a yellow dot. Now take a look at the beam. We have 3 different forces or loads, R sub A, R sub B, and 4 kips per foot. The vector R sub A is going through the yellow dot. It's going through point A. So the perpendicular distance between that vector and point A is 0, so we can neglect R sub A. However, we have to account for R sub B and 4 kips per foot. So let's do R sub B first. If I look at R sub B in comparison to point A, I see that that will cause a counterclockwise rotation. So counterclockwise rotation is equal to R sub B times the distance between point A and R sub B. That's 11 feet. Oops. Now let's take into account the 4 kips per foot times 4 feet, which is a 16 kip load. And we have to consider that the resultant of that load occurs right in the center of it. In other words, at 2 feet from point B. We can also see that relative to point A, that resultant force causes a clockwise moment. So let's tabulate it over here. Again, our force 4 kips per foot times 4 feet equals 16 kips. The distance between this resultant and point A is 11 feet plus 2, 13 feet. Now we note that we have accounted for all of our forces and reactions, so let's set these equivalent to each other. Run it through the calculator. We have 16 times 13 divided by 11 equals 18.91. Units, feet cancel, so our units are just kips. And that's all we can do, for sum of the moments. However, now we can come back and plug into this equation. 16 kips down equals R sub A up plus 18.91 kips up. Let's get the calculator, and we have 16 minus 18.91 equals negative 2.91. Negative 2.91 kips up. It's the same thing as saying 2.91 kips down. So we've determined that R sub A actually works in the downward direction. R sub B is still up. 2.91, 18.91. All right, let's continue with the shear diagram. We basically just look at all of the forces and reactions acting on the beam from left to right. So starting at point A, we have RA going down 2.91 kips. Between A and B, there is no load, there are no reactions, so I'm going to come straight across. At point B, I have an upward force, R sub B equals 18.91. Let's start with a negative 2.91, and we can add 18.91. We get positive 16. Kips. So now we've come up the 18.91 to a positive 16 kips, and the only forces left on the beam are the distributed load. 4 kips per foot times 4 feet equals 16 kips. Since this is a line load, the shear is going to be a sloping line. We go down 16 kips back to 0. We end at 0, and therefore we know we didn't make any mistakes. In order to do the moment diagram, I need to take these two areas. So let's call this one area 1, and let's call this one area 2. Now, area 1 is a rectangle. The formula for the area of a rectangle is base times height, or in our case, 2.91 kips times 11 feet equals 32.01 kip feet. And again, I'm computing areas. Area 1, area 2. Area 2 is a triangle, and the formula for the area of a triangle is base times height times 1/2. So our base is 4 feet, looking at the load diagram. Our height is 16 kips, and again, since it's a triangle, we have to divide by 2. 4 divided by 2 is 2, times 16 is 32. The units are kips times feet, 32 kip feet. Now, theoretically, these areas should be exactly the same. We have a small rounding error. This is because we rounded off the reactions. So for our purposes, let's just call it 32 kip feet for both of these areas. So to do our moment diagrams, we start at this connection on the left-hand side, and we know the moment is 0 at a roller support unless there was applied moment. We also know that this shear diagram area is negative, so we're going to be going down. How much are we going down? We're going the area of this orange area called 1, which is 32. So let's go down 32. Kip feet. And then from this point to the end, we have a positive area. And that area is also 32. So we go up 32 kip feet back to 0. Now we need to determine whether these lines are curved or sloped. Since the shear diagram is flat, we know the moment diagram is sloped. So we just have a simple line connecting those 2 points. Over here between these 2 points, the shear diagram is sloped. So we know the moment diagram must be curved. So we have to determine whether the moment diagram is curved concave up or smiley up, or concave down or frowning face. The way you determine that is by looking at the slope of the shear diagram. Going from left to right, this line is going downhill, so we know that we have a frowny face type curve. So there's our curve, and that's our moment diagram. Finally, we must find the deflected shape. We know that at the reactions A and B, we don't have any deflection or no displacement because these ends are being supported. We also know that the end is loaded, so we can intuitively understand that this is going to bend down. Then the backspan curves. That's the end of homework problem 4D.